We've been talking about Lewis structures. Sometimes you can draw more than one valid Lewis structure for a given compound or ion. So let's look at ozone and draw the Lewis structure for ozone. Well, ozone is O3, and in Chem 1A we don't make rings of atoms. There's no ring structures. We save that for OChem. So the only way to connect these three atoms is in a line. So we'll put oxygen dash oxygen dash oxygen. So the skeleton structure is the first step, and then we have to figure out, well, how many valence electrons to put in this structure. Each oxygen atom has 6, and there's 3 of them, so that gives us 18. So I already have 4 in there for the bonds. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18. So there's my 18 electrons. Does everyone have an octet? No, one atom does not. When we don't have enough electrons, then we need to share some more to give octets to everyone. So this is the atom that doesn't have the octet. So let's take a lone pair from this guy and share it with the other oxygen. So let's get these guys off. And we'll turn that pair into a bonding pair. Same number of electrons now. Now, each of these oxygens has an octet. This oxygen has an octet, 2, 4, 6, 8, 2, 4, 6, 8. Octets for everyone. Is there another structure we could draw that is extremely similar to that? I think of it this way. These oxygens are like children, perhaps. These may be triplets, identical triplets, right? So they're all oxygen, but are they all the same person? No, they are individuals. And so this oxygen got a double bond with the middle one. And this oxygen saying, why does he get the double bond? Why can't I have the double bond? Right? Well, why not? There's no good reason. So we can draw another structure where we just give the double bond to the oxygen on the other side. Does everybody have an octet? Yeah. Got the right number of electrons? So which of these is correct? Both and neither. What actually happens with ozone in nature is that the molecule exists as an average of these two Lewis structures. We can determine the length and the strength of the bonds in ozone. These Lewis structures predict that this is a double bond. It's going to be stronger and shorter than the single bond. But in reality, both of those bonds are equal in length and in strength, and they're intermediate between a double and a single bond. So you can kind of think of them as a 1.5 bond. So we represent that by drawing the two structures with a double-headed arrow between them. So I probably should have done all this drawing down at the bottom, but I did it up here. Oops. So I'll finish it up here. So we put a double-headed arrow between the two structures, and that indicates that the true structure is sort of an average of those. We call these resonance structures. Resonance always suggested to me that the molecule was alternating back and forth between these. That's actually not what's happening. The resonance hybrid, the average of them, is a little bit like what might happen if you have two different breeds of dog and they have puppies together, right? So here you've got a German Shepherd, and that looks like maybe a white lab. So they have a puppy, and the puppy might look like this. Does the puppy look like the German Shepherd one minute and the lab the next minute? Does it flash back and forth between them? No, that's silly, huh? Well, it'd be silly for the molecule to flash back and forth too. The hybrid, the child of these two different breeds, is a mixture of both of them. Okay? So when we look at Lewis structures, we can draw with the double bond, the oxygen on the left, the double bond with the oxygen on the right. But the true structure is more like this, where there's a 1.5 bond. Okay? I think of this as a little bit like my husband and I and our children. So this would be me. All of my ancestors came from Sweden. And this would be my husband. All of his ancestors came from Japan. And if you look at the kids, they all look amazingly alike, but they don't look exactly like either one of us. They're a mix, right? So a hybrid. Lewis structure does not do a good job of explaining resonance, okay? We're going to look at another model that can handle this. Lewis theory doesn't. But Lewis theory is so great and simple for so many other things that it's still very useful. So what's really happening here is in this ozone molecule, instead of the electrons being localized between the two atoms, they are actually delocalized, and they're spread out over the whole molecule. It's called resonance stabilization. So instead of the electrons just being shared between two atoms, they're actually shared over the entire molecule. This causes it to have a lower energy and causes it to be more stable than it would otherwise. Any questions about resonance? For the most part, you will only see resonance if you have a double or a triple bond that you can place between two different atoms of the same element. Okay, so if there's no double bonds, no triple bonds, there's no resonance in Chem 1A. Okay, just there isn't. So let's write a Lewis structure for the nitrite ion. Include resonance structures. So the way this ends up being worded on an exam is it could ask you to identify the different resonance structures, or it might ask you how many resonance structures does this thing have, this molecular ion. So writing the Lewis structure, we've got a nitrogen and 2 oxygens. General rule is the more electronegative ones go on the outside, and things also tend to be symmetrical. So we'll probably put the nitrogen in the middle and an oxygen on each side. We've got to pick something. Then we have to look at number of electrons, valence electrons. So the oxygen has 6, and the other oxygen has 6. We're up to 12. Nitrogen has 5, so that gives us 17. And then we have a negative charge, which means there's an extra electron. So we've got 18 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. And we're going to need brackets and a negative sign. Is this a good Lewis structure? What's missing? What's wrong with it? Everybody have an octet? No. The nitrogen doesn't have an octet, so that's not cool. We need to have more sharing. So the nitrogen saying, hey guys, this isn't working for me. I don't have 8 electrons. One of you has to share one of your lone pairs with me. So oxygen's like, I don't want to do it. I don't want to do it either. Well, somebody's got to do it, right? Which one? Well, we have the choice here, right? These are 2 atoms of the same element. They're both oxygen. One has to share, one doesn't have to share. This is where we end up with resonance. So let's just make the one on the left share. So that guy shares. We'll put that as a bonding pair. Whoops. Come on. And now we have octets. So the octet rule is satisfied. So we drew it with this oxygen sharing. Now we need to draw it again with the other oxygen sharing. And there could be 2 or 3 or 4 or even more possibilities for where the extra sharing or where the double bond goes. So we'll just draw it over here. So in this way of thinking about it, I'm going to draw the same not quite right Lewis structure. Over here, I made the one on the left share. He got the double bond. So over here, I'm going to make the one on the right share. So we'll move this lone pair in as a bonding pair. This also has a -1 charge. So I have 2 different versions. These are resonance structures, and so I draw both of them and I put a double-headed arrow between them. Any questions? We'll get some practice with this on the worksheet today. What the worksheet does is, instead of making you draw all of them, it just says, draw one of them and then indicate how many resonance structures there are. If there's only one possible structure, there's no resonance. So if you have resonance, the minimum is 2 resonance structures. Sometimes we draw Lewis structures, and we can draw several different versions that all satisfy the octet rule and all look great and everything. But, obviously one has to be better than the others, and how do we know which one is better? Formal charge is how we decide which one's better. Formal charge is a little bit like oxidation state in that it's a fictitious thing. It's something we made up to keep track of electrons. It doesn't reflect what's actually happening, but it helps us to predict what does happen. So the formal charge in a Lewis structure, you assign it for each individual atom, is the charge it would have if all the bonding electrons were shared equally between the bonded atoms. So I think of it as, okay, so you had these 2 things come together. We can, let's look at hydrogen and chlorine. So when hydrogen and chlorine come together and make a molecule, they each share 1 electron, right? You could think of this as hydrogen and chlorine getting married. And they each brought their own resources to the marriage, and then we're going to pretend that they're getting a divorce. They're splitting up. And when we do this, we're going to cut all the shared stuff equally. So I imagine drawing a line, we're cutting that bond. When we cut the bond, each bond is 2 electrons, we're going to give 1 electron to each atom. So the formal charge is looking at how many valence electrons did hydrogen bring in, and how many is it leaving with. We're going to take the number it brings and subtract the number it leaves with. That's going to give us the fictitious charge that atom would have if we were doing this. So for hydrogen brought in 1 electron and it's leaving with 1 electron, so its formal charge is 0. Chlorine brought in 7 and it would be leaving with 7, so its formal charge is 0. 0 formal charge is a good thing. So we're calculating these things completely ignoring electronegativity. This is how I prefer to think of it. The marriage divorce thing works when you're talking with 2 atoms. When you've got like 5 or 6 atoms and you're like, that's a pretty weird marriage, right? So then let's maybe think that we've got some business partners and they all invested in the company, and now we're dissolving the company and we're just cutting all the shared things equally and everybody's going their own way. You're going to compare what you brought in to what you're taking away. The way the book explains it, and if this works for you, go ahead and use it. The formal charge is the number of valence electrons that element has minus this total, the number of non-bonding electrons on that atom in the structure, and half of the bonding electrons. So this chlorine has 2, 4, 6 non-bonding electrons. There's 1 bond. There's 2 electrons in the bond. So half the bonds would be another 1 electron. My experience has been that most students don't like that method. They like just pictures better. So, of course, we've got to have some rules about formal charges. Like oxidation states, formal charges in a molecule or an ion add up to the overall charge on the molecule or ion. So if you have a neutral molecule, all the formal charges must add up to 0. If you have an ion, the formal charges add up to the charge on the ion. We are looking for small or 0 formal charges. 0 formal charges, or the smallest formal charges we can have, is the more stable Lewis structure. So we're trying to get everything 0. Sometimes you can't avoid formal charge. When that happens, give the negative formal charge to the more electronegative atom. The electronegative atom is the one that has more attraction for the electrons in the bond. And so if somebody's going to have electrons, extra electrons, it's going to be the more electronegative one. So let's look at HCN, that would be hydrogen cyanide, and see how this can help us figure out what's the best Lewis structure. So we've got, they're given to us here, but it's a little hard to see up there, so I'm going to draw them down here as well. So we could put the carbon in the middle and have a triple bond with the nitrogen, a single bond with the hydrogen. We could do it like that. Or we could put the nitrogen in the middle. What am I even looking at here? The nitrogen in the middle and the carbon on the end. How do you decide? Okay, so first of all, are those resonance structures? No. It looks like it's resonance, but the order in which these are connected is different. In a resonance structure, you're only moving a double or a triple bond. Here, carbon's in the middle between hydrogen and nitrogen. Over here, carbon's on the end, only bonded to nitrogen. These are different skeletal structures. The connections are different. This is not resonance, okay? So this is the book tabulating formal charges for us, but let's look at my method. So we're going to say, well, here we've got this structure, and we're going to just cut all the bonds in half and see what people leave with and see what they came in with. So we'll just cut that in half, and we'll cut that triple bond in half. Oh, I was going to do the one on the left first. I'll just do all of that first. So remember that each bond is 2 electrons. And if it helps, go ahead and draw those electrons in at the end of each line. So here, hydrogen, after we cut this bond, hydrogen's going to leave with 1 electron. How many electrons did hydrogen have before it became part of this? 1. So for hydrogen, we've got, that doesn't work. For hydrogen, well, I'm just going to write the H because colons or dashes, anything gets misinterpreted. Hydrogen has 1 valence electron. When it leaves this molecule, it takes 1 with it, and so that difference is 0. So this hydrogen is going to have a 0 formal charge. Carbon. How many electrons does carbon have, valence electrons, does carbon have by itself? It's the group number. 4. And when we break this up, carbon's going to leave with 1, 2, 3, 4, right? So 4 minus 4, 0. How many valence electrons does nitrogen have? 5. It's the group number. It's right up there. When this nitrogen leaves, it's going to take 1, 2, 3, 4, 5. 5 minus 5 is 0. So everybody ends up with a 0 formal charge. That means that this is probably the correct Lewis structure. Let's look at this one over here and see what happens. Well, again, hydrogen has one valence electron, and when it leaves this, it's going to take half of that bond, which is one electron. So that's going to have a zero formal charge. I'll do carbon next. Carbon has 4 valence electrons. When this carbon leaves, it's got 1, 2, 3, 4, 5. So 4 minus 5, that has a negative 1 formal charge. The nitrogen brought 5 electrons, 5 valence electrons to the structure. If we cut all the bonds in half, it's going to leave with 4. And so its formal charge is going to be plus 1. This is a neutral molecule. These formal charges add up to 0 in both cases because we have the correct number of electrons in our structure. But here, the formal charges are 0. Here, they are non-zero. So we're looking for the lowest formal charge that tells us this is the correct structure. Yes?
So then the formal charge could be used as like a check on your Lewis structure?
It can be used as a check on your Lewis structure. What we mostly use it for is when we've got 2 possibilities, and we use that to decide which is more likely.
Okay. And then like it's starting with the least electronegative one in the center, is it like 100% sure?
It's not 100%, but it's a good place to start. One of the frustrating things about doing this is I can't give you a set of rules that if you follow these steps, you'll always get the right thing. It's sort of a, okay, this is a good direction. It's like balancing equations, right? There's different ways to do it, and sometimes this one works, and sometimes that one works easier. So that's kind of frustrating. I think I talked to you about this. So let's look at hydrogen, carbon, and nitrogen as atoms. So if you look at the Lewis structure for the atom, hydrogen has 1 valence electron, carbon has 4, 1, 2, 3, 4. Nitrogen has 5, 1, 2, 3, 4, 5, right? And you put them around singly first, and then you pair them up. Looking at those Lewis structures tells me how to make a Lewis structure where these things are going to have 0 formal charges. Because they always get half the bonds. So hydrogen will have a 0 formal charge if it has 1 bond, because it has 1 unpaired electron. Hydrogen always has a 0 formal charge, right? It can't form 2 bonds, and it can't form 0 bonds, or it's not in there, so it always forms 1 bond. So you actually never have to look at hydrogen. Carbon has 4 unpaired electrons. When carbon makes 4 bonds, it will have a 0 formal charge. So we look here at this carbon, it's got 4 bonds, a triple over here and a single. That's good. So you need to know how to do this, but you can also look at this and avoid the math. So here carbon has 4 bonds, that's good. Nitrogen would like to have 3 bonds. 3 bonds in a lone pair. So here I've got nitrogen with an octet and 3 bonds, 0 formal charge. Over here nitrogen has 4 bonds and carbon has 3 bonds. That's not what they would like. And so they will have formal charges. Any questions? Okay, so assign formal charges to each atom in the 3 resonance forms of N2O. And here they're telling us that nitrogen is the central atom. That's not what we would necessarily predict. And we're being told that because we want to avoid having to draw all the other structures as well. So nitrogen is in the middle. So then let's see what we can do here. Oh, well, no, let's go back to blue. That blue. So nitrogen in the middle. We've got to put 1 nitrogen on this side. We put an oxygen on that side. Is there any other way that we can arrange those with nitrogen in the middle? Well, if you switch them around, you're just looking at it from the other side. So that's not actually anything different. So that's it, really. Nitrogen in the middle, nitrogen on one side, oxygen on the other side. So valence electrons, each nitrogen has 5. So we've got 2 times 5, and the oxygen has 6. So I believe that's 16. So let's put those guys around. We've got 4 in there already. 6, 8, 10, 12, 14, 16. We're short some electrons. So let's start moving things around and see what we can do. This guy's got an octet, so let's take one of his lone pairs and share it with the other with the nitrogen. Have the same number of electrons still. Now I've got an octet for the nitrogen in the middle, 2, 4, 6, 8, and for the oxygen, but the nitrogen on the end doesn't have an octet. So I need to do some more sharing. I want to take the lone pair from the central atom and share it with this nitrogen, because if I take one of these and share it, then I'm going to end up with too many electrons here. If I take one of these over there, that's going to be a mess too. So I'm going to take this lone pair and put it over here. You might have to do some trial and error experimenting before you end up with that. Does everybody have an octet there? Yeah. Is there a different way we could draw that? Okay, this is where we have to kind of think outside the box and open up our minds. So here I've got a double bond and a double bond. So apparently in this molecule I need a total of 4 bonds, but could I also do a single bond and a triple bond? Let's try. So we've got the same nitrogen in the middle, and I'm going to put 16 electrons, but now I'm going to start with the bonds and then fill things in. So I'm going to try putting a triple bond here. So I've got 2, 4, 6, 8, 10, 12, 14, 16. I can accomplish octets doing that, right? What about putting the triple bond on the other side with the oxygen? So 2, 4, 6, 8, 10, 12, 14, 16. We have the same arrangement of atoms. They're connected in the same order. We're moving the double bonds around, double single bonds around, triple bonds. These are resonance structures. They are not equivalent resonance structures, though. So we should put double-headed arrows in here. A little bit like, my husband and I and our children. One of these resonance structures contributes more to the correct structure than the other two. My husband's genes had more influence on what my children look like. I'm in there, but they look a lot more like him. So he's the dominant resonance form. Well, how do we decide? We look at formal charges. So let's just start with the one on the left. We're going to imagine cutting these bonds in half and then comparing what the atom brought to what it's leaving with. Just thinking about number of bonds, is this nitrogen going to have a 0 formal charge? How many bonds does it have? It has 2 bonds. Nitrogens like to have 5. This is not going to be a 0 formal charge. How about this nitrogen? It's got 4 bonds. That's not what it likes either, so that's not going to be 0. What about the oxygen? Is that going to be a 0 formal charge? Yeah. How am I doing that? I am looking at the Lewis structure for the individual atoms. So nitrogen and oxygen. Nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. Oxygen has 6. When you look at the number of unpaired electrons, that's how many bonds it will have if it's got a zero formal charge. Oxygen wants 2 bonds, nitrogen wants 3. So I can tell you that oxygen here has a zero formal charge without doing the math, but let's do the math anyway. So to look at this oxygen, we said, well, how many valence electrons does an oxygen atom have? And so that's 6 because it's in group 6A. And when we cut up this molecule, how many electrons is the oxygen going to leave with? 6. It's got this lone pair and that lone pair, and these shared electrons, we're just cutting down the middle. We're just sharing equally. We're not going to court and suing for more than, we're just going to say, okay, let's just 50% each, be done with it. So 6 minus 6 is 0. What do you know? The nitrogen in the middle, how many valence electrons does nitrogen have? It has 5. For this nitrogen, when we break up this molecule, how many electrons is it going to take with it? 4. 5 minus 4 is a positive 1. So this has a +1 formal charge. So we'll often indicate the formal charge is just writing a little number nearby. It gets kind of cluttered, so if it's a 0, just leave the 0 off. And then what about this nitrogen? Well, that nitrogen brought in 5, and how many is it leaving with? 2, 4, 5, 6. So that has a -1 formal charge. Okay, so we don't have 0 formal charges, but the formal charges add up to 0, so that's good. That says we probably calculated them correctly. So let's go over here. I can tell by looking at this that one of those atoms has a 0 formal charge. Does this nitrogen have a 0 formal charge? It does, because it has 3 bonds. And that's what nitrogen likes to have. Because when it has 3 bonds and you break the bonds and share those electrons equally, it's going to leave with 5 valence electrons, just like the 5 it brought in. So this one's going to be a 0. How about this nitrogen? It brought in 5, and how many is it going to leave with? It's going to leave with 4. So that's going to be a +1 formal charge. How about this oxygen? It brought 6. It's leaving with 7. So that's -1. Okay, so we still have a +1 and a -1. They're just in different places. And then let's look at this one. Is there anybody here who's going to have a 0 formal charge? No. Nitrogen wants 3 bonds. Neither of the nitrogens have that. Oxygen wants 2 bonds. It doesn't have that. So these are all going to have formal charges. So let's imagine cutting the bonds in half. The nitrogen on the left side came in with 5, and it's leaving with 7. So that's a -2. The one in the middle came in with 5, and it's leaving with 4. That's a +1. The oxygen brought 6, and it's leaving with 1, 2, 3, 4, 5. So this one has a -2 formal charge, a +1, and a +1. Any questions about how I got the formal charges? Okay. Now, how do we choose which one is going to contribute more? Which one's better? We want lower formal charges. This one has higher formal charges. We have a 2 and 2 1s. So you could think of taking the absolute value of the formal charges and adding them together, 2 and 1 and 1, that would give you overall a magnitude of 4. Whereas these 1 and 1 absolute value would be 2. So these are equivalent in terms of overall size of the formal charge. This one's bigger, and so that's not going to be the major resonance. And then how do we choose between these two? This is where we use the idea that if there's a negative formal charge, it's going to be more stable if it's on the more electronegative atom. Which is more electronegative, oxygen or nitrogen? Oxygen. So here, the negative formal charge is on the oxygen. That tells me that this is the most stable resonance form.
You said the lowest. You want the negative charge? The most?
On the more electronegative, yeah. So here we have a negative charge on nitrogen, here we have it on oxygen. Since oxygen is more electronegative, it is hogging electrons, it's really attractive to the electrons. So, if there's an imbalance, the negative charge is going to be on the more electronegative one. So this one in the middle is going to contribute the most to the correct structure. The other two will contribute somewhat, and we're not going to worry about how much or anything, but we should be able to draw all the different possibilities. Remember, when you're drawing resonance structures, the atoms stay in the same order. You can't suddenly put oxygen in the middle. That's not a resonance structure. That's just a different way of drawing something. That's a different structure altogether. You're just looking at moving the electrons around. Any questions? So let's draw the Lewis structure, including resonance structures for diazomethane. This is the formula, and they're telling us that carbon is central. So for each resonance structure, assign formal charges to all atoms that have formal charge. This time they're not asking us which is more important. They're just saying, draw these things and do the formal charges. My color's back. Well, carbon is central. So I put the carbon in the middle, and we're going to put the hydrogens and the nitrogens around the carbon. Let's try that. We've got a total of 4 for the carbon, 2 for the hydrogens, and 10 for the nitrogens, a total of 16 electrons to mess around with. So we've got 2, 4, 6, 8, 10, 12, 14, 16. Is that good? What's wrong? The nitrogens don't have octets. So then we need to share more electrons, right? So can I share this lone pair with the carbon? No. Carbon has an octet here. It can't share more. It's a period 2 element. We can't expand the octet. What are we going to do? Well, maybe we didn't connect the atoms correctly, because this obviously is just not working out at all. So carbon's in the middle, but does that necessarily mean that all of these have to be attached to the carbon? No. What if we put this hydrogen on one of the nitrogens? So I'm going to draw that over here. I didn't change the number of electrons. I just moved the hydrogen over. I did that because there was no way to write a decent Lewis structure the way I had them connected. Now I can take this lone pair on the nitrogen and share it with the carbon, because the carbon doesn't have an octet here. So I could take that and share it like this. So that's better, right? The hydrogens are good. They're easy to satisfy. The carbon's got four bonds, an octet. Nitrogen has an octet, but this nitrogen doesn't have an octet. I can't make this one work either, right? Because if I share this lone pair in here, then the carbon's got too many. So we're going to have to do the same thing we did earlier. We're going to have to move this hydrogen.
Can we also move the nitrogen to the side of the hydrogen?
Well, where would we move the nitrogen?
Well, see how like nitrogen and hydrogen are placed
Mm-hmm.
like that, but just like the reciprocal, on the opposite.
You mean just write them over here?
Yeah.
So, like this?
Yeah.
Yeah, that's actually the same as what I had drawn just now,
Okay.
just in a different position.
Okay.
So the thing about a Lewis structure is that these things are connected, but they're all kind of loose and jointed. And so if I move this one up to the side or draw it at the bottom, those aren't actually different. This looks neater. It looks more symmetrical. It looks nicer. But, you know, I kind of came at it a screwy way. This is a kind of a tricky one because, yeah, it says carbon is a central atom, but that makes you think that the hydrogens are on the carbons, and it turns out they aren't. So I would never give you this one on an exam. It's just a little too much. So I've shuffled things around. Let's check the electrons. 2, 4, 6, 8, 10, 12, 14, 16. Okay, I got the right number of electrons. Do I have an octet on everybody now? No, I don't. Carbon's missing an octet. So I can take a lone pair from the nitrogen and share. I'm going to take the one on the top just to keep it nice and symmetrical looking. Now they've got 8 on each, nitrogen, carbon, and nitrogen. So this is a little bit like the N2O that we looked at, where we had 2 double bonds. And it's not maybe obvious that you could draw 2 other resonance structures for this. You don't have to have 2 double bonds. You could have a single bond and a triple bond. So let's put these in the same order. Carbon, nitrogen, hydrogen, nitrogen, hydrogen. So we've got 2, 4, 6, 8, 10, 12, 14, 16. Oops. Has that got the right number of electrons and an octet for everybody? Yes, it does.
How does hydrogen come outside?
Hydrogen has a duet. Hydrogen never gets an octet. It's too small. So we kind of just ignore him because he breaks all the rules anyway. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. But why put the triple bond here? Why not put the triple bond there? No good reason. These are the 3 resonance structures for diazomethane. So we should draw double-headed arrows between them. And we're supposed to assign formal charges. Hydrogens are always 0. They got 1 bond, they're 0. Good. Let's look at this guy over here. This carbon has how many bonds in the structure? 4. That's what carbon likes, right? That carbon's going to have a 0 formal charge. The nitrogen here, an octet with 3 bonds, that's what nitrogen likes. And this nitrogen, an octet with 3 bonds. All 3 of these, nitrogen and carbon, they all have a 0 formal charge. You can do the math too, but it'll come out. So let's look at this guy over here. Here's a nitrogen with 4 bonds. That's not going to be 0. So let's figure it out. Nitrogen has 5 valence electrons. And if we cut up this molecule, cut all the bonds in half, nitrogen leaves with 4. So it's got a plus 4. So plus 1. 5 minus 4 is plus 1. How about the carbon? It's got 4 bonds. It's a 0. We're going to find that carbon almost always has 4 bonds and almost always has 0 formal charge. What about this nitrogen? Well, he came with 5, and how many would he leave with? 6. So that's going to be -1. It just asks us to write the non-zero formal charge. Because having 0 formal charge is not having a formal charge. This one also has formal charges. We actually don't have to do the math again, because really these are just switching situations, right? Nitrogen, 2 lone pairs, 2 bonds. This one is -1, and this one's +1. So of these 3, it doesn't ask this, but of these 3, which one's going to have more influence? The first one, because this has 0 formal charges. Any questions?